Today we are going over the integration technique partial fraction decomposition, and you would typically use this technique when you have an integral with a numerator and a denominator and your denominator is bigger than your numerator. And what I mean by that is the degrees of your denominator is bigger than your numerator, not just the size of it. And today we're going to showcase the three cases you would typically run into, which case one is when you just have two factors over here, which in this case is x minus 2 and x plus 1, and you would just split it up into a over x minus 2 and b over x plus 1. And basically how I like to think of it is you're assigning each factor with a letter. So x minus 2 is given the letter A and x plus 1 is given the letter B, which is literally what you are doing. The second case is basically when you have a power on your factor over here. So what you would do is notice how instead of assigning A to x cubed alone, you would just count from 1 to 3. So x to the 1, x to the 2, x to the 3, and each one of those would just have a letter assigned to it. So a over x, b over x squared, and c over x cubed. Now over here you notice on the second part you still have the 2x plus 1, which is also to the power of something, which is 2. So in this case you wouldn't just do 2x plus 1 squared and assign it to one letter. You would do 2x plus 1 and then 2x plus 1 squared, which is assigned to two different letters. And then in our third case is having an unfactorable quadratic form as shown in the ax squared plus bx plus c. So for example, over here it's x squared plus 9 instead of the squared being on the outside of the parentheses. So what you would do, instead of just assigning this to b and putting it over x squared plus 9, you would have to do bx plus c, which is assigning it to two different letters, which is b and c, and adding an x on the b. Now if you notice, this bx is basically here just to cancel out the x squared. That's how I like to think of it. I don't know if mathematically that is correct, but notice how if you divide bx over x squared, you will get a degree of -1. And so I will just demonstrate an example of each case you are given here, and let us begin. Oh, and also I forgot to mention, in case 3, make sure that you memorize this formula. You will encounter this integral a lot, which is the integral of 1 over x squared plus a squared, which if it looks familiar, it's because it is. It's from trigonometric substitution. And if you don't want to memorize it, you can always just u sub it, but this is a very helpful thing to memorize. It's just 1 over a inverse tangent x over a plus c. Okay, our first problem is going to be the integral of 7x minus 2 over x minus 2 times x plus 1 dx. Now typically the very first step I do when it comes to partial fraction decomposition is just take out the equation from the integral itself so that it's easier to just set it equal to your terms. So this is basically case 1. This is exactly case 1. We are just splitting it up and assigning to each letter alphabetically. So then we get a over x minus 2 plus b over x plus 1. And this is all just algebra. So our next step would just be to multiply both sides by the denominator of this first part, which is x minus 2 times x plus 1 on each side. On the left side, the denominator would just cancel out completely, and on the right side, you would just be left with a times x plus 1 plus b times x minus 2. Now the next thing you do is to try to get one of these values to equal 0. In this case, for a, we would just make x equal -1. So if x equals -1, our equation will become -7 minus 2 equals a times 0 plus b times -3, which if we simplify just gets us -9 equals -3b, which b becomes 3. So now we have one part. Now to find a, all we do is simply set x equal to 2, because look over here, if you set that to 2, that b would become nothing and you would just be left with trying to solve for a. So let's do that over here. If x equals 2, you would get 14 minus 2 equals 3a plus b times 0, which simplified just gets you 12 equals 3a. And now a equals 4. So now you may be wondering, okay, we know these variables, but now what do we do? Well, since this over here is equal to this, we could just use this part and plug in what we know. So originally we had the integral of 7x minus 2 over x minus 2 times x plus 1, but now we could just set it to the integral of a over x minus 2 plus b over x plus 1 dx. Again, due to this fact over here. So now we could just plug in our values, which is 4 over x minus 2 plus 3 over x plus 1. All I did was just substitute this a and b with what we got over here, which is just a fairly simple u sub, which you could probably just do in your head by now, which gets you 4 times the natural logarithm of the absolute value of x minus 2 plus 3 times the natural logarithm of the absolute value of x plus 1 plus c. And now you're done with your first partial fraction decomposition. And before we move on to our next one, my shortcut for this integral is basically just recognizing that the denominator has an x. So I just put that in the natural logarithm and then putting the the numerator in the front, and then just combining the two. I would now like you to do this second one on your own. Now remember, the first step is to take the equation out of the integral, which is 6x squared plus x minus 15 over x squared times x plus 3, and then try to assign a denominator with a letter, which remember, if we have a power in one of ours, we just put it in ascending order from the power of 1 to this number, which gets us a over x plus b over x squared, and then c over x plus 3. Now we could just multiply both sides by the denominator on the left, which is x squared times x plus 3, which then leaves you with just the numerator on the left side, and on the right side you just multiply each of these letters by this. So you were then left with a times x plus 3 plus b times x plus 3. And again, if you don't know what I'm doing, I'm basically just multiplying this by this and canceling it out with the denominator, and then using what's left, plus c times x squared. Now, it would be tedious to just do our old method, which is setting x equal to, for example, -3, which kind of disproves my point because this would cancel out everything, but let's just not use that, and instead, just distribute. And usually, how to determine when to distribute is when you have many variables like this. I like to do the x equals 2, x equals 3 method, or whatever, to cancel out to make zeros if there's only 2 variables, but in this case, we are given more than that, so let's just, again, distribute. After this, we are then left with this equation. So now what you do next is not very tricky, don't overthink it. Notice how over here we are given an x squared, an x, as well as a constant. Well, you're going to want to factor out each of these powers on the right side as well. So for example, there's an x squared over here, so let's try to get an x squared pulled out over here. Now what you want to do next is you want to look at which ones are multiplying by x squared. We clearly see that a over here is, so we're just going to put a in that parentheses, and we also see that c is, so we're going to put plus c as well. Now again, all I'm doing is taking this x squared out because it's correlating with this x squared over here, which I will show why is important later. And so based off this logic, now we're going to take out an x. So x times 3a plus b. And again, so far we've used up our terms ax squared, cx squared, 3ax, and bx. So now with our constant term, all we're left with is 3b. So let's write our left-hand side out. Now back to why this is important. This x squared is just going to cancel out this x squared. So we could get this 6, and we could get this a plus c and set it equal to each other. So 6 equals a plus c. Now based on this logic, this x cancels out, and this x cancels out. So now we're left with 1 equals 3a plus b. And again, with our constant, nothing really cancels out because it's a constant, so we're just going to set -15 equal to 3b. And I'll move these in a horizontal position, and now we just solve. So -15 equals 3b, well, all we get is b equals -5, and since we know b equals -5 now, we could just plug that in over here. So now we get 1 equals 3a minus 5, which equals 3a equals 6, which gets our a equal to 2. And now since we know a equals 2, we just plug that in over here. So that becomes 6 equals 2 plus c, and then c becomes 4. And now we are super close to finishing it. All we do is just plug that in to this equation. So our original integral equals a over x plus b over x squared plus c over x plus 3. Take the integral of that and put a dx. So now all we have to do is just plug in our ABC into this equation, which gets us the integral of 2 over x plus -5 over x squared plus 4 over x plus 3, and then dx. So now these become fairly straightforward integrals, with our 2 over x becoming 2 times the natural logarithm of x, the absolute value of x actually, plus 5 over x plus 4 times the natural logarithm of x plus 3 plus k. Now you might be wondering, why are we not using our constant c and why are we using a k? Well, that's because we already used up a c over here, so we don't want to get confused and think, oh, it's going to be plus c. Well then, it gets confusing because then couldn't you have said plus 4 since c equals 4 over here? And no, that's just not how that works. So just do plus k. Now our last problem is going to cover case 3, so it's the integral of 2x plus 17 over x plus 2 times x squared plus 9 dx. Now like always, we just take the equation out of the integral and assign each part of the denominator with a letter. Now notice over here, it's an x squared plus 9 inside the parentheses, so we're going to have to add b times x plus c. And again, that bx cancels out one of the x factors, so it just evens out at the end. And then you multiply both sides by the denominator, which will then leave you with 2x plus 17 equals a times x squared plus 9 plus bx plus c times x plus 2. And then you're going to want to distribute as well as FOIL all of these terms, which leaves you with all of this. Now you may be wondering, okay, there's an x squared over here and over here, but there's no x squared over here. Well, you would just assign a 0 with it because that's the same exact thing. You're not adding or removing anything. And then multiply that 0 again with the x squared. But again, before we do that, let's of course factor out all of our x squares, which is a and b. Let's factor out our x's, which is 2b and c, and then our constants, which is 9a plus 2c, and set that equal to the left side. Now, all we do is set 0 equal to a plus b, 2 equal to 2b plus c. Again, we're correlating these two and these two. And then 17 equal to 9a plus 2c. Now solving for each, you get a equals negative b, c equals 2 minus 2b. And the reason I solve for a and c is so we could plug that into here, which will get us 17 equals negative 9b plus 2 times 2 minus 2b, which we can distribute, giving us negative 13b equals 13, which leaves our b to equal negative 1. And now that we know that, we could plug that b into our negative b. Knowing that now, we could plug in this b into this b, which makes a equal positive 1. And also because we know that b, we could plug it into this b. So that makes c equal 4. Now knowing the fact that our original integral looks like this over here, we could just plug our variables in, giving us the integral of 1 over x plus 2. And a quick tip, if you have an x on the numerator as well as the denominator, you could always just split it up into something like this, a over x plus 2 plus bx over x squared plus 9 plus c over x squared plus 9. And that would be fine because it is exactly the same thing. We can then comfortably substitute, which is 1 over x plus 2 minus x over x squared plus 9 plus 4 over x squared plus 9 dx. Now remember when I said that you want to remember this integral right here, 1 over x squared plus a squared equals 1a inverse tangent x over a plus c. We can apply that to taking the integral of our problem over here. So we could do our usual integral step by step, with this becoming the natural logarithm of the absolute value of x plus 2. But then over here, you're going to want to find our a, which if you remember trigonometric substitution, a is simply just the square root of the value over here, which becomes 3, which if you remember from trigonometric substitution, a is just the square root of this value over here, which is 9, which simply makes a 3, and then plugging in those values. But before we get to using this formula, let's just solve for the second integral real quick, which becomes negative 1/2 natural logarithm of x squared plus 9. And then we could plug in over here, knowing if you remember trigonometric substitution, that our a would be the square root of this 9, which is simply just 3. And then of course plug in your constant in the numerator into the fraction 4/3 inverse tangent x over 3 plus c. And again, don't actually use plus c, use plus k, because we do actually have a c value over here. So just to recap on how to use this formula, just make sure you find your a value and you're set. And also if your numerator has a number such as this one having a 4 over here, simply just plug it in to this one over here, hence the 4/3. And that will wrap up the video.